Okay, so Chapter 6, which is what we're going to be doing, scheduled to be doing today, 6A and 6B, is on putting statistics to work. And 6A is on basically how to characterize data, how to find what a typical value would be, and a little bit about the shape of data. So first of all, I want to give you a definition, and that is a distribution. So the book defines a distribution of a variable or a data set, and when you see that term variable right there, just think data set. Okay, so the distribution of a data set talks about the way the values are spread out over all its possible values. And distribution can be shown visually with a table or a graph. And another definition, which is a little more intuitive, would be the following. A distribution is just a list of numbers. So when we talk about a distribution, we're usually thinking about just a list of numbers. So we can have the distribution of heights, distribution of weights, a distribution of, I don't know, just anything that you can keep a record of like that with numbers. That's what a distribution is. Now, how can we measure the center of a distribution? So this term right here, center, what do we mean by that? Think of center, that term right there, think of that as meaning a typical value. So when we talk about the center of a distribution, what we mean by that is, what's a typical value for the distribution? Another way that we say that, colloquially, is the word average. Okay, so average, the average of something is a measure of center or a typical value. Now, typically, when we just say average in everyday conversation, what we're talking about is the mean. But in statistics, average can mean the mean or the median or the mode. Okay, so an average can be any one of these. They're all ways to measure the center of a distribution or what a typical value is. So let's talk about those three ways briefly. So the mean of a distribution is what we most commonly call the average value, and it's defined as the mean is equal to the sum of all the values divided by the total number of values. In other words, you add up all your numbers and divide by how many there are. The median, when you hear median, think about the median of a highway. It's what's in the very middle of the highway. So the median is the middle value in the sorted data. And this is a very, very important thing. Sorted data. You always sort your data first before you calculate the median. Okay? So the median is the middle value of the sorted data. And I'll get into this parenthetical comment in just a second. And the mode is the most common value. It's whatever number shows up the most. So here's an example. So 8 grocery stores sell some made-up energy bar called the PR energy bar for the following, how many? 1, 2, 3, 4, 5, 6, 7, 8 different prices. Okay, so let's find the mean, median, and mode. So the mean is easy, right? You just add up all of the different prices, divide by 8, because that's how many there are, and you get $1.41. So the mean price is $1.41. That's all I'm going to say about the mean. The median. Now, here's where you have to think about how many values there are. In this case, there are an even number of values. So let me go back to that slide where I was talking about median. Or actually, let me just say it right here. There are an even number of values. So to find the median, you look at the very two middle ones. Okay, you look at the very two middle ones to find the median. And once you have the two middle ones, then you take the mean of those. Okay, the two middle ones are $1.35 and $1.39. So to find the median, you take the mean of these two. So the median is going to be $1.35 plus $1.39 divided by 2. So we get $1.37. This is the median. And then the mode is the most commonly occurring one. So if you look at all the different values up here, the only one that occurs more than once is 129. So that's the only one that occurs more than once, so that one is the mode. So I want to show you an example of a mode with an odd number of values. On the previous slide, we looked at the mode with an even number of values. So let's find the mode of these numbers. We'll assume that they're already sorted. Oops, I meant not mode. That's not what I care about. I want to do the median. So we'll assume these numbers are already sorted. So we'll take 2, 4, 7, 10, 12. So notice there are 1, 2, 3, 4, 5 different values. They're an odd number. So when there's an odd number, you just pick the very middle one. So the mode, I keep saying mode, I'm sorry. So the median is just 7, the one in the middle. So if they're an even number, the median is, you take the two in the middle and then take the mean of those two. And if there's an odd number, you just take the very center one. Okay, very briefly, let's talk about outliers and why we care about them. So an outlier is a data value that is much higher or much lower than almost all the other values. The example I always use is, let's just pretend all 5 of us are in class right now. If we look at all of our incomes, and then Bill Gates walks into the room, the average income of the 6 people, Marianella, Sabrina, Destiny, Theo, and myself, and then Bill Gates, our mean income would be, like $300,000 or $400,000 a year. But that's not a good measure of what a typical value is, because Bill Gates' income is an outlier. Okay? This is an even more extreme example. Here we have 5 pieces of data, $0, $0, $0, $0, $0, and $10 million. And you can picture Dr. Evil with his pinky on his face, is what I always do when I say this. $10 million. So the mean of all of these is 0 plus 0 plus 0 plus 0 plus 10 million divided by 5 is $2 million. So we're saying that the average, so to speak, the average contract offer is $2 million. Well, no. That doesn't represent most of the data. This outlier, 10 million, is affecting the mean. So that's why we care about outliers. The mean is pulled upward by outliers. Now notice, this is important, notice that the median and the mode are, that's an ugly color. Let me highlight that with a different color. The median and the mode of the data would not be affected by the outlier. If you calculate, and that's all I'll say, it's a good exercise to calculate the median and the mode of these two data sets so you can see that they wouldn't be affected. All right, let's look at another example. So, some newspaper surveys wages for assembly workers in some high-tech company and reports an average, look at that keyword there, average, an average of $22 an hour. The workers at one large firm immediately request a pay raise, claiming that their average wage is only $19. Again, notice we have this term average. The management says, nope. The management says they're overpaid because their average wage is in fact $23. So how can both sides be right? So the situation is some newspaper does a survey and finds, what an average salary is. Then the people who work in a similar firm say, hold on, we're making less than that, give us a raise. The management says, nope, you're overpaid. So how can how can the management and the workers both be right? Well, it's because they're using the word average, which isn't precise. Average just means typical value. So let's look at this next slide. So both sides can be right if they're using different definitions of average. That's kind of the key there. In this case, the workers may be using the median while the management is using the mean. Okay, for example, imagine there are 5 workers at the firm, and their wages are 19, 19, 19, 19, and 39. The median of these 5 is 19. The mode is also 19. That's what the worker said the average was. But the mean of those numbers is 23, as the management claimed. That's why we need to be really careful with what we mean by average. All right, shapes of distributions. So the only two we're really going to concern ourselves with are these unimodal, these distributions with one peak. These are called unimodal, and these distributions with 2 peaks, which are called bimodal. Okay. We also need to know, or I also want you to know a little bit about symmetry. A distribution is symmetric if you draw the line at the peak, it's a mirror image on both sides. This is a symmetric distribution. Okay? Distributions that are not symmetric must be more spread out. Okay? Must be more spread out, which means there's an outlier. If a distribution is spread out, then we say that it's skewed. Okay? A distribution that is not symmetric is skewed. So distributions will either be left skewed or right skewed. Okay? This can cause a little bit of confusion because people tend to look at over here where this hump is and they think, well, the hump is on the right, so it's right skewed. This hump is on the left, so it's less skewed. No, that's not how we think about it. Okay, you look at where the outliers are, and that's how we define skewness. Outliers over here on the left, on the low values, that's left skewed. Outliers on the right skewed. So another way to think about that is to see that there is a tail to the left. So it's left skewed. The other one has a tail to the right. So it's right skewed. So when you want to talk about which way it's skewed, you look at where the tail is of the distribution. Okay, a little bit more about symmetry. A single peak distribution is symmetric if its left half is a mirror image of its right half. A single peak distribution is left skewed if it's more spread out on the left side. That's where the tail is. It's right skewed if it's more spread out on the right side. There's a right tail. So these two examples, we're just going to talk about whether we would expect them to be symmetric, left skewed, or right skewed. The first one is A, heights of a sample of 100 women. Second one, number of books read during the school year by 5th graders. And speeds of cars on a road where there's a visible patrol car. Okay, so take a minute, go ahead and pause the video and take a minute and think about whether you think these would be symmetric, left skewed, or right skewed. The distribution of heights of women is symmetric because roughly equal numbers of women are taller and shorter than the mean. And really, really tall people and really, really short people are both really rare. So the heights are probably going to be symmetric. And that's true for men too. That's true for a lot of things. Heights and weights and things like that are usually symmetric distributions. Now, the fifth graders reading books, these are going to be right-skewed, okay? Because most fifth grade children read a few books during the year, but there are always a few kids, and I was one of them, who just read a whole lot of books. So there'll be a few outliers who read a lot more books. So this is going to be a right-skewed distribution. And then for the cars, drivers are going to slow down when they know that there's a patrol car looking for speeders. Okay, so you're not going to have anybody going really fast. But some are going to be really below the speed limit. So this distribution is going to be left skewed. And then variation is the next thing after measures of center and symmetry. Variation tells how the data is spread out. Okay, so distribution can either have low variation, where it's just real tightly packed in right here, moderate variation, where it's kind of normal, and then high variation, where it's very, very, very spread out. Okay, so we go from low to medium to high variation, and this is what the pictures look like. And then how would you expect the symmetry and variation to differ between the Olympic marathon and the New York marathon? So again, before you look at the answer, it might be good to pause the video and think a little bit. But basically, in the Olympic marathon, everybody's a good runner. Okay, they're all going to be good runners in the Olympic marathon. So there's going to be very low variation and probably symmetric. In the New York marathon, though, anybody can try the New York marathon. Runners of all abilities can do there. So it's going to be very, very high variation for the New York marathon. Olympic marathon would be shaped like this. All right, probably symmetric with low variation. And excuse me, yeah, an Olympic marathon. And the New York marathon would be spread out like this. Lots of variation. So that's that. And that's all for this section.